Where's my chat button? Cool. So, welcome. I have a much smaller crowd than usual tonight. For those who are joining us, I see um, only one new name tonight. Matt, thanks for joining us. For those who are not familiar with how these, um, this is the Tucson Amateur Astronomy's fundamental group. We meet every second Thursday of the month, and this meeting typically has two presentations, sometimes one, depending on volunteer availability. So tonight we will be in the one category, having just the one presentation. Tonight we are having a follow-up to a presentation that I put together in December on galaxy classification. This is the second and final part to that, where we'll finish up with some of the more niche galaxy types, but that are still potentially interest of us as amateurs. Yeah, I wouldn't want to be in Minnesota right now either for that temperature weather, Scott. So, without a further interruption, if you do have questions on them, you can feel free to speak them as they come to your mind or type them in the chat. My setup might mean that the chat doesn't get answered as quickly, but I'll do my best. So, in December, we tonight, sorry. Um, so the first part of this presentation will just be recapping some of the critical things from the December presentation, particularly about the Hubble Galaxy Classification System. That'll take a little bit of time, hopefully not too much. My goal is to kind of skim through that section, and then we'll get right into it with all of the interesting subclasses that we can find of the various types of galaxies that we know about. This is not an exhaustive list of subclasses. These are just some of the more interesting and less, hey, you need to have a degree in astrophysics for some of these to really make sense to you categories. So, without further wait, recapping of the Hubble system. So, when Hubble was first starting out, back in the 1920s with his landmark papers, where he helped establish that the universe was expanding, which he had also uh, determined that the Andromeda Galaxy was in fact another galaxy. Part of this work he spent building up, if these galaxies are different objects, let's go and try to categorize them. And that's what he did for about 10 years from when he, over the course of a 10-year period, eventually coming up with four major galaxy groups. These are what's known as a morphology system, which is basically we're categorizing the appearance of the galaxy and not necessarily any of its other properties like spectral emissions or so on. Uh, so it's purely just you look at the galaxy, what does it look like? And we wound up with four distinct classes: uh, spiral galaxies, irregular galaxies, which you can see over on the right and the inside, lenticular galaxies, which are here in the laser pointer, which are here in the center of this classification diagram, and ellipticals. Being a morphology system, this is a subjective system, which means that sometimes things get misclassified or maybe reclassified as more data becomes available. And people say, wait a second, this doesn't look like that. So it's not in some cases, not a hard or fast rule. This has also led to some other alterations to the system and try to make it less more of a subjective system and more objective. But it's still, again, mostly a grad student had to look at a picture of the galaxy and said, yep, that's a spiral or not.
Question.
Go for it.
That is a very old chart, and I think at one point they thought it was an evolutionary chart.
So that it's It is, but it isn't. That was one of the subjects that we talked about in the last meeting, which I'll be skipping over on this one. If you are interested in more about what I talked about those sections, the recording of that full presentation, which I'm only recapping on parts of here, is on our YouTube channel, Matt.
That's great. Thank you very much.
Now, we also briefly talked about the distinction between what astronomers refer to as early type galaxies and late type galaxies, with really this designation more referring to uh, how much material or how is left in the galaxy for in terms of forming stars, which is indirectly but not necessarily tied to their age. And as I mentioned here, regulars or late type galaxies, which they're still forming new stars. It's kind of one of those weird systems where you have to just sit there and think about it sometimes. And uh, but that particular designation won't really come into play here for much of this. We and then we spent time going through each of the four main Hubble types. A regular galaxy is establishing that these are the oddballs of the group. They don't really fit into any of the other three main classification systems. And also kind of separating them from peculiar galaxies, which we'll talk about at the very end of this presentation. We listed some common examples that we might see of irregular galaxies, as here being Messier 82 and the two Magellanic Clouds in the southern hemisphere. We talked about ellipticals and how these are uh, the blob versions of galaxies, and they are generally formed from the merger of one or of at least two, sometimes more galaxies that were at one point spirals. And the original view saying from Hubble was that ellipticals evolved into spirals, and we now know it's actually the opposite, that spirals evolved into ellipticals through the collision process. And we talked about as we saw on that slide way back that on that chart, how there's different number categorizations and how the different elliptical galaxies, how those numbers fit into the classification systems, with E0 galaxies being more circular and E7 galaxies on the far end being the more ellipsoidal. Here we see over on the right. Next, we rose to lenticular galaxies, which we saw on that diagram is they are kind of the midpoint between elliptical galaxies and spiral galaxies, but not necessarily an evolutionary standpoint. And how these are more of these look kind of like spiral galaxies. There's some elements that they share, but there's also elements of ellipticals. So they were certainly that midpoint between those two groups. And how we could sometimes not determine whether or not a galaxy is a lenticular or a spiral depending on its orientation. Again, circling back to that visual aspect of the Hubble system and why it can sometimes be ambiguous in the classification if you can't see, if you're looking at a galaxy on its side, like say M104, you might not necessarily be able to distinctly say, yes, that's a spiral galaxy. Just you don't, because you need to see more of the galaxy's face in order to make some of those judgment calls. We presented some distinct versions of the lenticular galaxy, kind of highlighting how this one here, you can see there is some of the spiral structure. It does seem to have a spin to it, but it's not really what astronomers might term as well defined if you compare it to other spirals. And then lastly, we wound into the spiral galaxies, which are generally, as we as amateurs, are some of the more prettier objects to look at in the night sky if you do like galaxies, especially the face-on spiral galaxies. We talked about how these are, well-defined cores with two, sometimes more arms, and all the characteristics about them, and how they are further split into three different categories of spirals, namely unbarred spirals, intermediate spirals, and barred spirals. And what the individual things that separated those three classes apart. And As a reference, here are some examples, some more prominent examples of spiral galaxies between a uh, between two of the declinations, whose numbers escape me at this particular point in terms of which one SA and SA. I think SA is just an unbarred spiral, and SABC is an intermediate spiral, if I remember correctly off the top of my head. And that's it for the Hubble system that we just needed to blow through tonight, just kind of as a quick refresher on that. Any quick questions or comments before I continue on? Okay, now into the new stuff for tonight. We'll start off with dwarf galaxies, which we did sort of talk about where in the beginning with irregular galaxies, namely the large and small Magellanic Clouds. But these are the most common type of galaxy in our universe, which is so kind of makes sense. You know, we normally would expect that even if you look at how our stars are formed, we expect the small stars, such as the M-class red dwarfs, are more populous than the larger stars, such as the O and B-class giants. It was a similar sort of thing with galaxies. The dwarf galaxies tend to outnumber the larger galaxies by quite a bit. Now, what just separates these from the mainline large galaxies is, you know, by their namesake, they are low in mass. They don't emit a lot of light, which can make them hard to detect at great distances. Mm. And they typically have a small physical size. In fact, the smallest known dwarf galaxy is SIGU 2, which has a total mass of about 550 solar masses, which puts it at slightly less size than the globular cluster Omega Centauri in our own galaxy. So there is sometimes a little bit of ambiguity. Um, there originally was an ambiguity of whether or not dwarf galaxies were, in fact, just globular clusters orbiting their host galaxy or not. And we eventually separated out with a combination of spectroscopy in order to determine whether or not it is a globular cluster or a dwarf galaxy. Some other quick facts about SIGU-2 that I was able to turn up before we move on is that it is a fairly old galaxy. It's about 12 billion years old, which is roughly a little bit slightly younger than our Milky Way. It has 100% fewer heavy elements than the sun, so it is a very metal poor galaxy, which most of its stars are red dwarfs. So they're very long-lived stars. There hasn't been a lot of supernova within this dwarf galaxy to churn out these heavier elements that would potentially lead to planet formation or metal-rich stars like our sun, which is an interesting factor because it has what's known as an integrated luminosity of about 800 times the mass of our 800 times the light of our sun. This is basically astronomers speak for saying if you take the light out of the whole area that we can see for this particular galaxy and you summed up over each of the pixels, uh, it's about 800 times the sun, despite having 500,000 solar masses. So that also tells us it's a very diffuse object as well. Moving on back to spirals, these are also share many of the same primary classes of the Hubble system. Dwarf galaxies can fall into the category of ellipticals, they can be spirals, and they can be irregulars. But we don't have the lenticular classification for spiral galaxies, and instead they swap that out with a spheroidal class, i.e., these are basically sphere galaxies as they appear to us, which which to me also can be maybe a little bit misleading between spheroidal galaxies and elliptical galaxies because they're both tried to denote the roundness. So I'm not quite sure what astronomers used in order to separate out those two. I wasn't able to find anything definitive on that. To give an illustration of just how much more popular they can be, uh, the local galaxy cluster that the Milky Way is a part of has three main members: the Milky Way galaxy, the Andromeda galaxy, and the Triangulum galaxy. And every other galaxy in our current local group is the dwarf galaxy. And there are about 36 of those. Most of the light that we see that was emitted by our galaxy cluster comes from the three main members. And the rest of the remaining 10% of the light that we we throw off in the universe is from our companion dwarf galaxies. These galaxies also further, in addition to having their own subclassification, there's also some things in dwarf galaxies that set them apart spectrographically, or they have other interesting characteristics that you wouldn't necessarily see in a larger galaxy, which we'll talk about two of these here. We'll talk about I, two of these special subclasses. I can't remember the names off the top of my head. I have to go look at my slides. This is a picture that some people have seen before. This is just a rough illustration of our local galactic neighborhood. And as we can see here on this, you only see M33, M31, and the Milky Way here, and everything else within this central sphere. And I don't know if the best you guys can see up here. This is a 5 million light here thing. The team's bars in the way. I don't. You should be able to see that though. This central sphere is roughly 5 million light years across. As we can see, there's most of these are falling into the dwarf categories because this is representation of the local group. And then out here we have a lot more of the larger galaxies in the NGC system, and so on. Dwarf galaxies also have are still considered a very active target of modern research. There is a bit of a puzzle with them in terms of the number of dwarf galaxies that we observe versus the number that our computer simulations of the evolution of the universe predict. For example, the most computer simulations, when they try to uh, estimate the evolution of our galaxy and how the Milky Way and our local group may have formed, predict that our own galaxy should have about 500 dwarf galaxy companions. At present, we have only 11 known. There's kind of this debate. Well, not kind of. There is a debate in terms of what actually is the cause of this discrepancy. Are we just were these galaxies just because of the quirk of physics just gobbled up by our companion galaxies over time, or is there something within simulations themselves that's biasing into these? We haven't quite ruled it out. Uh, One of the main suspects is that dark matter and our understanding of dark matter is one of the main culprits here, since dwarf galaxies tend to have a very high dark matter to a regular matter content compared to large galaxies with not almost 99.99% dark matter in a dwarf galaxy compared to 90 to 95%. So that 5%, that 10 to 5 to 10% difference in dark matter content certainly is significant for astronomers to help understand. Moving on to the first subclass of dwarf galaxies that we'll talk about, we were talking about blue compact dwarf galaxies. These are galaxies that are dwarf galaxies that are undergoing a very high rate of star formation. They are a subclass of starburst galaxies, which we'll also talk about here later tonight. And when they were first detected in sky surveys, they were originally thought that these were some of the younger galaxies that were forming their first stars. They didn't have a lot of metals in them, so they were, relatively close to the metal content that we might see out of galaxies forming in the early universe, despite some of these galaxies being very close to us. But we aren't quite, so that's they're interested to professional astronomers for that reason, in terms of hoping to understand some of the mechanics of early star formation in the universe back when we didn't have a lot of metals and there were still mostly hydrogen, helium, and lithium in the universe. The primary trigger mechanisms that we think are the cause of blue compact dwarfs is actually galaxy mergers between multiple dwarf galaxies instead of a dwarf galaxy merging with a larger companion. Or gravitational interaction. So we certainly think at this point that these aren't galaxies forming their first stars, rather they're under the effects of their neighbors, and it's why they're having these increased rates of star formation. This is an example of a blue compact dwarf galaxy. This one's in Ursa Major. This is a recent James Webb photo. This is IZW10. If you, but this is certainly probably not an object that we would be able to go and reasonably look at with anything of our gear. With James Webb here pulling out a lot with its incredible optics. And as we can see in here, there is a lot of blue star formation. So many young bright stars. And I'm not quite sure if this outer gas envelope here is local gas in between us and the galaxy, or if this was part of the galaxy. It's kind of hard for me to make that determination just looking at this without more information. We then move on to ultra faint dwarf galaxies. These are the second class of that we'll talk about for dwarfs before we move on to other objects. These were first detected in the Sloan Digital Sky Survey in the early 2000s, and these are very low mass dwarf galaxies. As we saw, um, well, low populations. As I did say earlier, with that Sugiyo 2 galaxy having a mass of 550,000 sols, um, but so it does have some very large stars in it. Versus ultra faint dwarfs, they have a limit on the number of stars within here, containing about 100,000 counts. So difference here between mass versus counts for that Sugiyo 2 dwarf galaxy I mentioned earlier. And these are galaxies that are detected at extreme distances. They are typically found in the way distant at great distances from us in the 12 to 13 billion light year range, which puts them in the period of what's known as reionization, which is just another step in the evolution of our universe back in its early history. So this means that as part of this consequence, it seems that many of these ultra faint dwarf galaxies ceased their star formation. So they've been kind of in this stagnant, steady state since the period of reionization, which also means that most of these stars that we do see are very old or likely to be red dwarfs like M-class stars or K-class stars, which allows them to live for a very long time, which contributes to the galaxy's overall faintness. For those who aren't familiar, M dwarfs are very, very faint stars, even by our standards. Uh, so they do not put out a lot of light overall. Um, Kind of hinting back earlier to that distinction between what we know between a dwarf galaxy and a globular cluster. This is probably measured just by looking at how much dark matter um, is we think around the object. Since we can't detect dark matter visually or through any other measurements, we have to kind of infer its existence based on gravitational effects. And so that's sort of what we do with these galaxies. We look at how the individual stars, that if we can resolve them with our instruments, given their great distances, and use that to kind of make that decision. Hey, are we looking at a globular cluster or not? The main thing here is that ultra faint dwarfs are very heavily dominated by dark matter, and in fact, a majority of the galaxy, even more than that 99.99% figure I cited earlier for regular dwarf galaxies, these have more dark matter than that. Although I wasn't able to find an exact percentage figure, but they are uh, heavily dominated by dark matter as well, contributing more to that offset between this Sugiyo figure of like solar mass versus luminosity. Questions or comments? Okie dokie. There we go. So we'll circle back now onto some more interesting subclasses of spiral galaxies. We did briefly mention that there were the three main classes of spiral galaxies being barred, unbarred, and intermediate spirals. We'll talk a little bit about some um, non-visual classifications of spiral galaxies that are interesting in their own right. We first find here with anemic spirals. These are spirals that are in this sort of mid-range between what we think a lenticular galaxy should be and any of the other spiral galaxies should be. But what makes these interesting is that they don't have they are hence their name anemic. They don't actually have any significant star formation going on within their boundaries, which is a characteristic that we normally attribute to elliptical galaxies. But they still maintain a strong signatures of spiral arms uh, or other spiral structure, which separates them apart from lenticulars, which they're generally lacking in a spiral, well-defined spiral arm structure. This these part of this helps makes it so that they're kind of challenging to separate. You do have to do a lot of spectroscopy on the galaxy in order to say like, hey, what's the star formation rate within this galaxy to classify it as an anemic galaxy or not. So there's certainly probably more of these out there than that we've currently found. Um, and we are normally we would attribute to a lack of star formation as caused by uh, interacting galaxies within it. So gliding the parent galaxy, taking another galaxy, and that triggering star formation that exhausts the gas early on in the galaxy's life, which is what normally would lead to an elliptical. We don't necessarily think that's the case with these. What one theory that I was able to turn up is says that what really happened here is that um, a large number of globular clusters around these galaxies. I think some of these had like an order of like 2 to 4,000 globular clusters in their neighborhood. Took Was able to pull off a lot of the gas that would have otherwise been used by star formation early on in the galaxy's life, and so that's what led it into this sort of anemic state. This is an example of how some of these compare. These are all fairly faint galaxies, uh, at least that are pulled up here in this example. There are anemic galaxies that are closer to us that we would be able to image. I just don't have a hand image example for one that we could potentially look at with our own equipment. But this does serve as an interesting point here in that how they can be difficult to detect. Uh, as we can see here from the top, we have these normal active spirals. They do look overall a little bit bluer, which is a hint of, having younger stars, bluer stars in the star forming regions contributing to that blue shade, while anemic spirals are definitely more on the red side here, which we would expect from having a lot more low mass stars in that overall range. But again, you would need spectroscopy usually to figure out whether or not, in order to generally separate these two at a more granular detail rather than having just somebody look at like, well, this is an anemic and this is not. Moving on to the next classification of spirals, we wind up at what's known as passive spirals. These are in some ways related to anemics. There's still some active study going on in these. We're not quite sure if they are distinct objects. These are typical galaxies that are observed at very high redshifts, which means that these are galaxies that are very, very far away from us, typically in very large or very populous galaxy clusters. But what's odd about them is that that as best we can tell, these galaxies lack stars larger than 20 solar masses, which is very odd. So this is essentially saying, I think the cutoff for this is at the end of A class stars, and then B and O class stars are higher than 20 solar masses. So from our standpoint in our galaxy, I think the figure for B and O class stars make about like 9% of all the total stars. These galaxies have almost none of those. And we aren't quite sure the exact reasoning for these in terms of how an entire galaxy would just utterly lack the materials to form stars this massive. It is quite an interesting puzzle. But regardless of having theories here to explain what's triggering what the underlying mechanisms behind passive spirals are, there is some thought that this is a step in the transition phase between a lenticular galaxy and a spiral galaxy. Although some of this is kind of iffy if that actually is the case. Again, active research areas. Sometimes you can only find so much. without running into paywalls of journal articles and things like that. Any questions before I move on to our move out of the spiral galaxies, finishing this up here. Okay. And next we wind up with, sorry, text messaging. With starburst galaxies, these are a category that we might be a little bit more familiar with, mostly because of our good friend Messier 82, which is a very bright object in the night sky, which is one of the more prominent examples of a starburst galaxy. Hence, by their namesake, these are galaxies that are just experiencing a very high rate of star formation. By astronomer terms, they classify this as forming about 100 solar masses of new stars per year. So this could be anywhere from, hey, we're forming 100 new M-class stars per year, or any smattering of the gamma between like, well, here's a couple of very large A or B class stars. So it's not, we're not saying here it's forming 100 new stars per year. It's based on the mass of the stars forming. So not to compare that with our own galaxy, the Milky Way is itself forming roughly 3 solar masses of new stars per year. So at least from what we've been able to determine in the limited range of the Milky Way that we can observe. This rapid increase in star formation will lead to the galaxy exhausting the majority of the gas and dust that it can use to form stars in a very quote unquote short time frame. And these are typically the result of having a spiral galaxy or a lenticular galaxy merge with, one or more dwarf companions, or have a near gravitational miss, like in the case of M82, where 2 galaxies kind of graze past each other, and we see at this elevated rate of star formation. This leads to a lot of red and blue colorings in the galaxy, and the blue coming from the larger class stars that are getting formed by this process. So here are 2 examples that many people are likely familiar with. We have on the left M82, which is an example of a starburst galaxy that was caused by a near miss. So the larger galaxy Messier 81 passing by M82 in the distant past triggered this rapid burst of star formation within the host with M82. And on the right, we have the antennae galaxies. And I thought that image is an image is a lot blurrier than I was expecting it to be. I apologize for that. Is the antenna galaxies, which are 2 galaxies that are currently undergoing a merger process. And so we see all throughout it these bright red zones all throughout the galaxy pairs of just gas that's undergoing collapse to form new stars. Many starburst galaxies are typically irregular or spiral galaxies. They are also sometimes fall into several other subclassifications. So you'll have a spiral galaxy that's a starburst galaxy. That also is a blue compact galaxy, or it's a luminous infrared galaxy. So, again, multiple classifications or extended classifications for the same galaxy are certainly possible here. The starburst galaxies, at least 2 varieties. There's more that are that we can get into, but for the sake of time, we won't. Are 2 blue compact galaxies. Give me one second. Excuse me. These are starburst galaxies that are low metal, low dust content. Dust typically just being this material residing between galaxies, not between galaxies, but in the interstellar regions of the own galaxy that's used to form planets and other materials. But they also have a very high population of massive young blue stars, which is what gives them which contributes to their namesake of being a blue compact galaxy. And then from there, we have luminous infrared galaxies, which are our second class of starburst galaxies. These are very, very high in dust content, and I don't think I have pictures of these. I think I have a slide that's out of order here. I think I do. Ooh, I'm gonna have to come back to that. Sorry. uh, luminous infrared galaxies, they're very high in dust content. So this massive star formation we see within that galaxy, normally these young bright stars like O and B and A class are emitting a lot of light in the UV spectrum and the X-ray, and sometimes higher end of the X-ray spectrum, but not always. But the amount of dust in this galaxy absorbs a lot of that higher energy light, and it will re-emit it out as infrared, which is so hence the name of these galaxies. Mm, that's why that's okay. And what was an interesting fact is that the brightest galaxy we currently know about is a luminous infrared galaxy slash quasar. And this one galaxy, or multiple galaxies, which I'll explain here in a second, is emitting the amount of light in infrared of about 300 trillion suns, which is a staggering amount of light when you consider that our whole galaxy has about 2 to 400 billion stars in it. Uh, which leads to an interesting puzzle of like what we think is going on when why is this galaxy so luminous in infrared? And this is a picture on the right of this particular quasar slash luminous infrared galaxy that was found in WISE data, as we see over here on the right. We have this central bright galaxy and these two other galaxies here to the left and kind of upper left of center. It looks like when we have trails of dust leading all the way back into the central companion. So it certainly does look like this is not one singular object, but possibly three or more galaxies undergoing a merge, which contributes to the overall um, process of this just the high dust content in this particular region, and well, the sheer amount of light that's getting resolved here. We think again, when you're staring at tiny blobs on telescope lights, there's only so much you can determine with spectral without. It's a lot of work. But that was a really cool little object I found when researching that. Next, we wind up with Seyfert galaxies. These are also one that you might be a little bit more familiar with if you're especially here in Tucson during the spring and fall. Not spring, in the early spring, where we get this look at Centaurus A before it sets into the summer skies. These are a class of galaxies. They were first observed by astronomer Vestos Slipher, who we've talked previously on uh, our Astronomer of the Month series. But they weren't necessarily classified, understood for what they were at the time. And it took an astronomer known as Carl Safer to formally say, hey, these are distinct objects or interesting objects in the overall scheme of galaxy classifications. Seyfert galaxies are one of the two main types of what we term as active galaxies or galaxies with an active galactic nucleus. The other classification are the examples of active galaxies are quasars slash blazars, which we'll talk about here next. And we currently, by current estimates, Seyfert galaxies account for 10% of all the galaxies that we can see. These are typically spiral galaxies, but not always. Sometimes you can get a lenticular or an irregular galaxy that is exhibiting the characteristics of a Seyfert class active nucleus. Most of the light from these galaxies comes outside of the visible light bands, which is um, why these weren't necessarily recognized as distinct objects in the beginning, because we needed radio telescopes in order to make sense of these. And Vesto Slifer didn't have access to those that type of equipment during his time because he was operating before the 1950s when radio astronomy began to actually become a serious, a new form of observation. What's interesting about these objects is that their overall brightness, uh, well, there's a lot of things interesting about these, but the main thing that we typically measure on for galaxies is the amount of energy or light that they are giving off across the various bands, and it can actually change very, very quickly on astronomical time scales, sometimes shifting within changing its overall brightness within the period of 1 or 2 years, sometimes faster. But there are plenty of examples that we can actually look at in the night sky. Several of the several of the galaxies that we can see on the Messier list are in fact Seyfert galaxies, with M51, the larger companion of M51 being the Seyfert galaxy, M64, M66, and Canis Venatici, and Canis Minor. Yeah, Canis Minor that we see in the spring. So most of these galaxies, we can actually, the first three galaxies, we'll actually be able to look up here as they start getting higher and higher in the sky as springtime approaches. M81 and M88 as well, and M106. Three of those, so four of those are in the Ursa Major region, being Seyfert galaxies that we can go look at with reasonable equipment, although we can't necessarily make out their distinctions. Now, as I hinted at earlier, with Centaurus A being the uh, more common example that we see of a Seyfert galaxy, at least when they're talked about in when I go out to CAC or Tempa, usually talked about Centaurus A just because it's a pretty object to look at. This is not a pure image of Centaurus A. I like this because it was an image looking at how the magnetic fields change across the galaxy, which is why it looks like we have a lot of these line objects throughout the galaxy. These are measurizations of the light polarization, which tells us things about the magnetic fields of the galaxy, which is just a really cool way to visualize this effect. But Centaurus A is an active, as a Seyfert galaxy. It does have an active galactic nucleus, which we'll talk about what exactly that is here in a moment. So I've mentioned this a few times. I've never actually given it a formal definition of what exactly is an active galactic nucleus. What causes Seyfert galaxies? What is their trigger mechanism? And it's just a side effect of the galaxy's central supermassive black hole eating. Gas that is in the region of the supermassive black hole will tend to, is actively being consumed or falling into this very dense supermassive black hole. As it does this, there's only sometimes this gas material can only be eaten so quickly, and so it will build up in the vicinity of the black hole while it waits to be eaten, and this causes the material to accelerate, and this produces friction, which gives off light. Uh, what this separates Seyfert galaxies from their much brighter companions of quasars is that the amount of light that is given off by a Seyfert galaxy as it consumes this gas does not exceed the brightness of the rest of the galaxy, which is what a quasar does. The feeding activity of the supermassive black hole in a quasar dominates the rest of the light in a quasar. uh, Seyferts are typically divided into two different subclasses, which is generally used to just segregate, are these Seyferts that are emitting high amounts of X-rays and UV, or are these Seyferts emitting high amounts of infrared, which is the main separation here. What was For those who are a little bit more into the physics side of things, these galaxies do exhibit what are known as forbidden spectral lines, which is a bit of a misnomer in here. But this is a physics/quantum mechanics aspect where we are trying to say It's not necessarily forbidden. What happens for those who are familiar with spectroscopy, when we say, hey, this light is high in hydrogen alpha emission lines and hydrogen beta emission lines, this is just a specific frequency of light that is being given off by a hydrogen atom, which we see reflected back at us. What happens in a forbidden spectral line is it's just a very, 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 very rare transition for that electron to emit specific light at a specific frequency, on the order of like one in several million odds of having this particular spectral line. So it's not necessarily forbidden. It's just, well, it's very low statistical odds. But still one of those cool things for those that are more interested in spectroscopy and some of the weird natures of that particular field. And now we wind up at the brighter companions of active galactic nucleus, quasars and blazars. As I kind of hinted at a second ago, these are some of the brightest objects in the universe. We can clearly see them way across the galaxy, way across the universe. We originally thought that they were actually just very bright stars, but what set them apart was they had very large amounts of radio emissions, which was why they were their namesake. Quasar is just a portmanteau of quasi-stellar radio source, indicating just their nature of detection being primarily originally in the radio wave bands. And as I did previously mention, these are an active galactic nucleus type galaxy, but they separated parts from Seyferts, and having the light of the light of the feeding activity of the black hole exceeds the light of the rest of the stars in the galaxy. I'll show you what that looks like here in a second. Most of these quasars are very distant in the 8 to 11 billion light year range. So very on in early universe's history, was a potential phase of just a normal galaxy evolution, as the galaxy itself maybe starts funneling gas towards the supermassive black hole and enters more of a stable phase over time. So eventually the quasar phase will itself terminate and shut off as the uh, supermassive black hole runs out of material to feed. So it is a temporary state of the galaxy. It's not a permanent condition. Blazars are related to quasars, being we just think that the difference that separates them is that with a blazar, the polar jets from the supermassive black hole are pointed directly at us, whereas on some quasars, the polar jets from the supermassive black hole are pointed not away from us, but just not directly at us. So here's an example of a quasar you could potentially go look at here in the springtime as Virgo gets higher in the night sky. You'll probably need to be at a very dark sky to see it. It does have and probably with a moderate size Dob or Newtonian, probably in the 10 to 10 inch or higher range. But this is the quasar 3C 273. And as you can see by its name here, it does look very much like a very bright star. But this is actually the entirety of a whole galaxy, just shining really, really brightly. This is the closest quasar to Earth at about 2.3 billion light years. And so from this photographic plate here, which you can see, you have some faint galaxies here in the background in this quasar, which is probably as far or not farther than some of these other galaxies that we might see here in the background, is just outshining the rest of them. So giving context here and just how bright some of these quasars can be and why their names are, how they got to their names. So still one of those cool things like, hey, let's go look at these next time you might be out here in the spring. So quasars were first detected at the beginnings of radio astronomy in the early 1950s. We couldn't being a very young field, there wasn't some of the abilities to correlate what we were seeing with radio astronomy with optical bands. Um, we couldn't necessarily see 12 billion years, 12 billion light years away with equipment in the 1950s like we could today with Hubble or later telescopes that came online in the 80s and 90s. And so there was a bit of uncertainty about, hey, about what these objects actually were at the time. But contributing to that was that quasars, like Seyferts, could change their brightness on very short timescales, or in the case of they were detecting in time, change the amount of radio emissions that they were emitting on very short timescales. And in some cases, these changes were observed over the period of days or weeks. So, more of that. We aren't quite sure what these are yet until we could get better data. It is also thought that the Milky Way itself might have gone through a quasar phase in the distant past. We aren't quite sure on that. There's some debate on whether or not our supermassive black hole companion, Sagittarius A star, is massive enough to create the forces necessary to uh, trigger a quasar behavior, but it could very well have gone through a Seyfert phase multiple times as it devours light material because you don't quasars don't need nearly as much. Well, quasars need a lot more gas and mass in gas in the region of the supermassive black hole, in addition to a larger supermassive black hole to make them as bright as they go. Seyferts don't need to have those restrictions. So we might have been a Seyfert. Who knows? Uh, mm, so I've kind of talked about this a little bit. Seyferts, quasars like Seyferts are caused by the same fundamental physics of a supermassive black hole eating a lot of material, or a lot of material falling into the supermassive black hole and heating up. But in the case of a quasar, this material will accelerate greatly as it sits there and waits to be fed on, sometimes accelerating itself anywhere from 10 to 80% the speed of light as it sits there waiting around the black hole. Uh, okay. During this process, as the black hole devours this gas, about 6 to 30% of the material of this mass gets converted back into pure energy, into light, making the process that which powers quasars more more efficient at mass to energy conversion than nuclear fusion that goes on inside of stars. So I think our sun has efficiency of like 0.5% on the mass to light conversion in its core was, I think, the figure I saw. So much more efficient than that with a supermassive black hole when you throw that guy in the mix. And as I also did mention, acceleration, as this gas loiters around the black hole and accelerates, it's friction that is causing this gas to heat up and emit the illumination that we see.
Just a quick question, if you don't mind.
Mm-hmm. Go ahead for it, Bernie.
That the conversion to energy being more efficient than the sun's fusion, is that still called fusion then, or is there another name given to that higher level of conversion?
So with this mass, it's not a fusion process. What's happening is because with fusion, you're basically taking, mass, squeezing it, and it's emitting energy in the form of radiation as part of that fusion process, where you might be giving off where
Yeah,
like a
I'm
neutron
saying
or so,
fusion. I'm just
but
wondering if
with
this conversion has a different name.
I did not see a specific name for it. I think it's
Okay.
a technical name for it, but if that answers your specific question.
The you don't know the name. Okay, that's fine. I
Okay.
was just curious. Perhaps there isn't a name for it. Who knows?
Mm.
Sorry to break
No,
your concentration.
no, you're fine. I just wanted to make sure I understood the question that you're asking and was answering it. the best I could. Mm. Uh, but what's also interesting about quasars is, like the other galaxies, they themselves can merge. And as we have here in these examples of two quasars, these are two pairs of two quasars that are actively undergoing a merge. These are not the same set, so this is one pair of quasars merging, and this is another pair of quasars merging, which is uh, something that was really cool. You don't necessarily anticipate. It's not. I didn't see if that the merger process that these two pairs were undergoing was part of what triggered the quasar phase, which is certainly possible. As you know, the merger process of two galaxies will direct gas from one supermassive from the galaxy into the supermassive black hole of the colliding companion. So it is possible, certainly possible that the quasar phase was triggered by the merge process rather than being quasars before the merger started. But in addition to mergers, quasars can also be found in groups. They are not, standalone solitary galaxies within their respective galaxy clusters. And in fact, what it was, we're not quite sure I was understanding what some of the articles were saying is that quasar groupings are part of what are some of the larger structures in the universe, such as galactic filaments and super galaxy superclusters. So it's not quite sure how they were organizing uh, the quasar groupings, of whether or not these were just multiple quasars in the same supercluster, or how that was being um, um, cataloged and separated out. It wasn't quite clear to me on what that distinction was. Uh, but nonetheless, they do exist. You can have what was notable is that there is a huge LGQ, which is interesting. I think the L stands for large quasar group. Uh, that also might be autocorrect might have also hit me there on the huge portion. I think it might have been Hoig or another German name rather than being huge per se. But it was a quasar group that contained 74 quasars, which spread out over a 2 billion light year area, which is part of what made me confused researching this of is this a group or is there just 74 quasars inside of a supercluster? So kind of confusing as to how that's actually being expressed. So this is just another expression of a quasar across from our good friend James Webb, showing how quasars change over time with and how they emit light at different spectrums and how that correlates to how fast the material is moving. So here we have a Hubble picture of a quasar. This is a James Webb trying to get a closer up view. And the different colors here are corresponding to the, I think this is, if I was interpreting this correctly, this is the speed of the material, with negative being the material moving away from us versus and positive being the material moving towards us, which is why you can have a negative velocity here. And how that's relating to the production of ionized hydrogen in the region of the quasar. So just one of those cool pictures. So sometimes it's rather more about the topic. We're like, hey, here's this really cool picture of something. And finishing up, we arrive at peculiar galaxies, which is the last group of objects we'll talk about for tonight for galaxy classification. These are some of the more like some of the Seyfert galaxies we talked about. These are some of the objects that we can potentially see. Well, not depending on the object, can see with reasonable amateur gear. For example, the antenna galaxies, being a peculiar galaxy, are one example that we can go out and see with our own equipment. Although you would generally need a sizable scope to to see significant detail on some of these objects or astro imaging as well, but reasonable. These are a subclass of regular galaxies, which are galaxies that are either interacting, are not usually a single galaxy, but two galaxies or more that are either interacting with each other gravitationally or undergoing a merge process.
Question.
Yes, Matt.
Um, I've known about ARP galaxies. You know, I thought it was a name of an astronomer, not a acronym. And if it is an acronym, I wonder uh, which astronomer or group of astronomers.
It
Uh,
the ARPS did
there
come
was
from were cataloged by a single astronomer whose name I'm double checking here because I did not write it down.
may have been an ARP.
I don't think that was his last name.
No, well, I know that he was. Yeah. I recall that it was one astronomer that was cataloging them.
Oh no, yeah, it is his last name. You were correct. Holton ARP.
Isn't that weird?
Yeah. So Atlas of Peculiar Galaxies is just the name of the catalog, but its designation that they use for the abbreviation is ARP after the creator's name, after
Right.
the original astronomer, the
So
original
he's
cloud cataloger's name. Excuse me.
yeah, he's in the pantheon of famous astronomers of the 20th century because of it.
Mm.
You know, he's if you're into astronomy history, you know about this guy. Thank you.
So Peculiar galaxies, as we did see very early on in this presentation, we would have galaxies classified as like an E0 or an SA0 or an SA3, denoting whether or not, hey, this is an elliptical or a spiral galaxy or an intermediate galaxy. These will additionally be added with a P or PEC onto the classification. So like an SAB0P for this is intermediate spiral galaxy of low arm density, but it's also a Purcury galaxy. Um, there's an incomplete bullet that I forgot to finish. Oops, or take out. So this is a more interesting example of Purcury galaxies. This is ESO 162-17 in the constellation Carina. So not a galaxy that we can see here from Tucson, but it was more of a highlight to me in that I don't think this galaxy is, without looking at a more wider field picture here, this is certainly not a galaxy undergoing a merge process, but it might be a galaxy that has had a gravitational interaction, which is what which is what made it one of the candidates for inclusion in the ARP catalog for peculiar galaxies. But you could certainly, so you're not necessarily expecting on all of these to say, hey, these are galaxies colliding. That's certainly not the case, as we can see here at this one. But, mm, excuse me. So don't always associate peculiar galaxies with merging galaxies, which is what we might expect when you go look at the antenna galaxies and you're, hey, this is the antenna galaxies are in the ARP catalog. Well, they must all be merging. Not true. And as I did misspeak earlier because I forgot about this particular entry. Well, yes, this should be the real last set of galaxies. These, finishing this up with what are known as Type CD galaxies. These were one I found very late yesterday. Well, that is, so this is hastily thrown together. These are a subclass of elliptical galaxies, and they are also termed supergiant elliptical galaxies. These are very, very massive galaxies, uh, or they have a very large uh, diameter of some of these being 1 million light years in diameter or larger compared to the 110,000 light years for our Milky Way. So these are ellipticals that are at least 8 to 10 times larger than our own galaxy in terms of uh, overall size, not necessarily mass. I'm not quite sure where they fall on the mass spectrum because you could potentially have a elliptical galaxy that is very spread out, but also very diffuse. So, very spread out, but might still have the same mass. So, didn't really see any readily available statistics on that. The C designation is just used to indicate that the galaxy is very large. The D component is for diffuse. And the CD is a holdover from a galaxy classification system we did not talk about, known as the Yerkes classification system, which is not generally used anymore except for the CD classification and one other. Hmm. The CD type galaxies are generally found at the center of galaxy clusters, and their positioning tells us that these are ellipticals that have likely undergone multiple mergers over the course of their history. And in fact, some of these galaxies that we've been able to define that they have multiple galactic nuclei. That means they have multiple supermassive black holes within them that we've been able to distinctly detect. Uh, but one potential one that you could go look at here later in the spring, probably sometimes best around the April or May timeframe, is a galaxy known as ESO 383-76. This has uh, an apparent diameter of about 1.8 million light years. That's not distance from us, that's the galaxy's actual diameter. And it's located in the constellation of Centaurus with an apparent magnitude of 11.2. But it is a very small object. So this whole field of view is about 5 arc minutes. So we would likely need to use something like the 40-inch Dobsonian that we have at CAC in order to make anything out of this. And even then, it might still just be a really bright smudge. Despite its location in Centaurus, it is actually located at the deck band of -32, which puts it about 10 degrees higher in altitude than Centaurus A, which is about -45 on the declination. So certainly an object that is, not low in the gutter like Omega Centauri and Centaurus A. Uh, so uh, should be less strainful to go look at from our location here in Arizona. Definitely something we might go look at. Who knows? And after that, I have about 5 pages of Wikipedia references and other references used for making this presentation. And this presentation will also be uploaded onto a Google Drive for those who might be more interested in looking at some of the references for this. Any
Okay.
any questions or comments from anybody? This is
Just
the
to
end point
kind
here.
of comment, we're in a second golden age of astronomy right now due to the advent of the JWST and the HST and the soon to be commissioned Nancy Grace Roman telescope. But anyways, what's been in the news is the little red dots. They're termed little red dots, and they're showing up on JWST images. The reach of the JWST is going even farther back in history. And from what I've read, which isn't a lot, uh, the news media says that, oh, this is going to upset the entire astronomy community and on how the universe formed and all that. As I understand it, the surprise is that the little red dots are larger than what they expected. And they're so far away, I'm not sure how they're going to classify them, perhaps by just spectral characteristics.
So little red dots, which Matt is referring to, These are very, their name essentially comes because they show up as little red dots. They are galaxies at very, very high redshifts, meaning
There you
essentially that
go.
they are very, very young galaxies. I think and on average, they're being seen as they were 300 million years or less after the Big Bang, which is uh, the main conundrum with them is how did these galaxies get this much material this early on in their lives? Uh, is
Right.
is what's contributing to the mystery that he is referring to.
And we have to be careful, as usual, with what the mainstream media reports it as versus what the astronomers are saying. To me, and this is something that I do religiously, when something comes out in the media, even and also in astronomy magazines and whatnot, I look at the original papers and read the abstracts because a lot of times that information is taken out of context to sensationalize the story. So, but again, it's amazing that we are in a second golden age of astronomy, and it's a lot of fun to uh, read about it, and it's just certainly amazing.
And with that, I'm going to go ahead and end the recording here. And thanks, everybody. I assume there's no more questions before I pause the recording. Tom, you usually have a couple of questions. I'm waiting. Besides
Yeah,
the turnover and saw you waiting, coming off mute.
yeah. Actually, a couple of simple ones. Early on, you were talking about the blue dwarf galaxies, and I
Blue
think something else
compact
was,
dwarfs. Let
yeah.
me.
I presume you mean blue as in color blue, not necessarily like blue shift, right? Which,
Correct. Blue is in color blue coming from the blue color of the young star of the O and B class stars that are being formed within these galaxies. Because as I did mention, blue compact dwarfs are a starburst galaxy, so they are undergoing star formation. This is not um, blue shift or red shift.
yeah,
Blue
yeah.
shift
Oh,
being, they're coming towards us. It's not related to that
right. That
that measurement.
Okay, yeah, that's what I thought. Um, the other question about the blue color though is you said they don't have much in the way of metals, so I presume they're mostly hydrogen and helium or something like that. Um, I'm not sure what the spectrum is for hydrogen or helium for that matter, but I presume they're blue because there seems to be a lot of that line, however many
So
nanometers,
when we
angstroms,
when we
whatever it is.
typically talk about the coloring within a star specifically, it's not referring to um, the blue itself is not referring to, hey, this is all blue from hydrogen. It's referring to the temperature of the stars themselves in this context.
Ah,
So
gotcha.
blue is referring to these are very hot stars,
Gotcha.
not
Right.
necessarily these. The blue is saying, hey, this is, lots of hydrogen. You have to actually look farther with spectrographic tools to say, hey, this is a lot of blue light, but what is the actual individual spectrum that it's made of in order to
Gotcha.
see what the actual metal content of the star is?
Okay. That makes a little more sense to me. Okay. The other question I have for you is you mentioned models with dark matter included, and I think you said something like there should be 500 dwarf galaxies in our local group or something. Whatever it was you said there.
Hmm?
Um, I certainly didn't learn about dark matter until I don't remember 1980s or something when we started hearing about that. Um, were there models before? And I'm curious what the models before they included matter might have said about how many dwarf galaxies there should be.
So it's very hard. What running these types of simulations that simulate a micro universe take a very, very large amount of computational power, like supercomputer level
Yeah,
computation.
yeah, assume
So
so.
with these sorts of simulations didn't really become practical for us until like at least readily available to a majority of astronomers until the mid 2000s, where as computer costs dropped. So between the advent of dark matter and sorting trying to figure out what it actually is over the from its detection into like the early 2000s, that certainly wasn't part of the overall cosmology models. We didn't know where it fit. We didn't know what the mathematics of that was until the last 15, 20 years as the computational powers allowed us to add that in. So I don't think there were computer models powerful enough in order to say, hey, here's how a local segment of the universe evolves like we have today.
Right. Yeah. Okay. Okay. I kind of wondered about that because I didn't really I didn't really hear much about dark matter in terms of uh, quantities of galaxies. I pretty much only heard about dark matter in terms of trying to figure out the spin of a spiral. Um,
So that was how we've completely changing topics here. Uh, and it's probably worthwhile that we might just do a presentation on dark matter. I don't think we actually have, or if we have, it was really more of the history of dark matter rather than some of the more advanced side of it, which might be one of those things that's inappropriate for this group because given the depth of knowledge that it takes to sometimes explain this. But dark matter was first speculated at or hinted at based on observing the rotation of spiral galaxies, and that, hey, these stars should, if we from normal gravity, these stars should be flying away. They aren't. What gives? Hey, there's
Can
more
I
mass here.
interject?
Let me finish, Matt.
Sure, sure.
And so that was what first clued us into the potential presence of dark matter. But dark matter, because it's such a significant, we now believe it's such a significant component of every galaxy, as I said on some of these slides, anywhere between 90% or more of the overall mass of a galaxy itself. The distribution of dark matter throughout the universe as it evolved is what sort of directs normal matter into the clumps that have formed galaxies. And so as this dark matter is sort of indirectly driving mass into these forms, the simulation is saying, hey, if dark matter is this thing and it's pushing mass in this way or controlling mass in this way to form these galaxies, we would have the simulations are showing there should be more of this stuff here. Why isn't there? Is it a problem with the models? Is there something else that we're seeing that we cannot see because of our proximity to like in this particular slide, the Milky Way in question, to say, hey, where are all these things? Well, we ate them. So you can't really see that anymore. That's part of the mystery here with the dwarf galaxies.
cool.
You were saying,
Okay,
Matt?
Yeah.
okay. The thing I'm into astronomy history, and I recently, well, I've known for years. I've known the daughter of Fritz Zwicky, and there's a book uh, at the Central Library in Phoenix, and it is the first tome about Fritz Zwicky and his life. I think the Wikipedia entry even says that he's the one that came up with the uh, discovery, I guess you could say, of dark matter. And I recently read a book in paperback. If you guys don't mind, I can go grab it and show you the cover. It's not that old, but it has, to me, it's the latest tome on dark matter. I can go grab the book and read you guys the title, the
So,
ISBN.
so just a quick clarification here.
Yeah.
Zwicky didn't discover dark matter. He postulated its existence based off of not any observational evidence, but really more of mathematical theory. It wasn't
Ah,
until he coined the name, but it wasn't like went out and discovered it. We didn't really discover it until much later by looking at the behavior of spiral galaxies. So it's really more of a, hey, I theorize this thing exists, and then somebody came back and said, hey, we actually found this thing. Hey, this guy said it might exist. So depending on your view of which one is the actual discovery is, subjective matter to me.
okay. I was thinking about composing a lecture about Fritz Zwicky, and I have one right now for E. Bernard that I've developed over the years. I find that
Yeah. If
part of
you are
the,
interested in presenting on Fritz Zwicky, Matt, go ahead and send
yeah,
me an invite. It's not send me, send me an email. And what month you would like to present it on, and we can go ahead and certainly squeeze you in. I mean,
well,
I don't really have any other
right,
presenters, so by all means.
right now, the only one I have is the one on Edward Emerson Bernard. It's about a 45-minute PowerPoint. I need to get off my duff and go
I
get that
we,
book
we
at the
recently did a
library.
presentation on Bernard, so I don't think we want to represent him so soon. When did we do him?
Well, I have it's a very in-depth. I did a lot of research on that one.
We not do. When did we do Bernard? I know we did him. I think I was the one who did him. Yeah, we did him in uh last April, April 2023.
Wow. Well, the last Star TMC, I did the presentation there, and a number of the clubs in the LA area. They even wanted me to
But
give it at the Griffith Observatory, but I didn't have the transportation for that.
if you're willing to, I think since we've already had this topic, we'd probably be more interested in the wiki presentation. So whenever you feel comfortable that you have material to present, reach out to me. We can certainly
Well,
get you in.
that would uh, give me the impetus to really do this.
Yep.
It takes a lot of work, to research
Mhm.
presentations. Not as bad as writing a book,